So let's imagine that we've got a container here, and it's got some length L right here. And we've got molecules in here bouncing around all over the place. And so I want to think about this a little bit. And I say, well, let me think and say, well, what is this? Okay, so when the molecules bounce off of this wall right here, they exert a force on it. So we know that the force is going to be the change in momentum over time. Okay, well, if the molecule is moving this way, it's got momentum mv. If it's going that way, it's minus mv, so the change in momentum is going to be equal to 2mv. I'm going to take the absolute value of that. Now, the time is going to be the time, if you imagine just one molecule going back and forth, then one molecule, it bounces off one side, goes to the other side, comes back. So the time is going to be the distance over, or rather the distance divided by the speed. Okay, well, the distance is 2L divided by V. Okay, and so what we get here is that the force for one molecule is going to be equal to mv squared over L. Okay. Now, the next question, though, is, well, if we have n molecules in here, how many of them are going back and forth this way, as opposed to up and down or in and out? Okay, and so they're all moving in different directions, so we can imagine that about 1/3 of them. So we can say that the total force will be n over 3 times mv squared over L. Okay. So that kind of gives us an idea of this. Now, in this case, the v is now going to be the average velocity. Okay, so this is not necessarily the v of individual molecules, because now they're all moving differently, so it's going to be the average in there. All right, now, next thing we want to think about, though, is that we look at this, we've got the average velocity in here, and so n mv average squared over 3L, okay, pressure is, imagine this thing being a cube, so L versus L, so pressure is force over area. Okay, so the area will be the area of this side right there. Okay, so that means this is going to be nmv average squared over 3LA. Well, L times A is volume. So this is nmva squared over 3 times volume. Well, if I multiply through, pressure times volume equals n over 3 mv a squared. Okay. Well, wait a minute. We also know that pressure times volume for a physicist is the number of atoms times the Boltzmann constant times temperature. Okay. So I plug that in here, then we say that in K sub BT is going to be equal to N times mv average squared over 3. The n's cancel. So I can multiply through kbt, 3 times kbt equals mva squared. Divide by 2. So if I divide this by 2, 3/2 kt is equal to 1/2 mva squared. That's the average kinetic energy. So that means the average kinetic energy of the molecules is 3/2 times the Boltzmann constant times temperature measured in Kelvin. Okay, So now we have the relationship. We kept saying that the temperature is related to the average kinetic energy. Now we know what the relationship is. 3/2 times the Boltzmann constant times the temperature in Kelvin. That is going to be the kinetic energy. All right, so this will now finally relate to kinetic energy. So this is what we call the kinetic theory of gas. And it's interesting because we know that kinetic energy, 3/2 kT, that's equal to 1/2 mv squared. And so that means if you have a whole bunch of gases here, like the Earth's atmosphere is mostly oxygen, got some nitrogen, there's a few occasional hydrogen and helium atoms and so forth like that in the atmosphere. And so what happens though is that they're all bouncing off of each other, so they're all the same temperature. So they're all the same temperature here, but they have different masses. So the low mass ones have to be going faster than the high mass ones. And so what that means is that the low mass ones, if you actually look at what's happening here and make a graph of the velocity, remember the average velocity is here, so again, average velocity, but it's going to be a bell curve, and part of that bell curve is going to be above the escape velocity. So that means, for the heavy ones, it's going to be much lower here, so not as many of them escape, but hydrogen and helium, the two most abundant gases in the universe, turn out to achieve escape velocity. Helium is very rare on Earth. It's kind of funny we play with the stuff because we don't really make helium. You can set off a hydrogen bomb, it makes a little bit of helium. A little bit of radioactive decay produces helium, but none of those things are really good ways of making helium. And so, what happens is that what helium we have on Earth is pretty much the helium that Earth has. And so when you play with it, when it gets out of a balloon or something, it floats to the top of the atmosphere, achieves escape velocity, and then leaves. And so that's why Earth's atmosphere is mostly oxygen and nitrogen. You go to like Jupiter, Saturn, Uranus, or Neptune, they have more gravity, so the escape velocity is further out. And so they're able to hold on to hydrogen and helium. In fact, their atmospheres are mostly hydrogen and helium. So we call those worlds gas giants. Mars has even less of an atmosphere than Earth does because it has much less gravity. And so ultraviolet light will actually break apart these things into individual atoms, and those individual atoms can achieve escape velocity and leave. So Mars can't really hold on to an atmosphere. Doesn't have quite enough gravity to do that. And so that's an application of this concept right here. And it's kind of interesting. The other thing is we know that 3/2 kT, this is related to gases, ideal gases. So this is related to the average kinetic energy, but it also relates, to some other sort of things here. It's similar sort of concept for other objects. So even with a liquid, you have a liquid right here, and the molecules are bouncing off of each other, and so some gain energy, some lose energy. So if you were to make a graph of the number that are a particular energy, then it would look something kind of like that, just like with a gas. Now, the interesting thing is that some of these are going to be going fast enough that they can pull away. In other words, they'll have enough energy as if they were boiling away. So that's evaporation. So even though the average energy defined by the temperature of this object is well below the boiling point, a few molecules can get away. Now, question, what happens to the average if you take away the big numbers? The average drops. So that's how evaporation cools things. Okay. So that's how your body, even if it's over 100 degrees out, your body keeps cool by evaporating water. And so the evaporating water takes some of that heat away and keeps your body below ambient temperature. Normally, heat wants to go from hot to cool, but the evaporation keeps you cooler than the temperature outside, but it has to work at it. So that's why, 99 degrees feels really hot, because that's just above body temperature. 99 degrees feels quite a bit hotter than 98 degrees. 100 degrees feels even hotter than 99 degrees. 101 feels even hotter than that. So each degree, when you're at those kind of temperatures, has a much larger percentage effect on your body than, for example, going between 74 and 75 degrees. That's really not as huge of a difference on your body. And so this is what goes on. And of course, if you already have molecules in the air, they're bumping into the ones trying to leave, and they suppress this. So the higher the humidity, then the less evaporation goes on, and so the less effective this is at cooling you. Again, all this gets back to applications of physics. And so, unfortunately, we're out of time for the semester, so I don't have time to go through all that. But it would be really cool to go through all these applications of thermodynamics and explain the physics as to how all this stuff works.